Welcome to this problem-solving session. Today, we'll be tackling an exciting problem: longest continuous subarray with absolute diff less than or equal to limit. This problem is a great opportunity to strengthen your understanding of sliding window techniques and array manipulation. Let's dive in and explore the approaches together. In this problem, we are tasked with finding the length of the longest contiguous subarray where the absolute difference between the maximum and minimum values in the subarray is less than or equal to a given limit. A subarray, as you may know, is simply a continuous portion of an array. The absolute difference is calculated as the positive difference between the maximum and minimum values, regardless of their order. For instance, if the maximum value is 8 and the minimum is 3, the absolute difference would be 5. The goal is to identify the longest subarray that satisfies this condition. If no such subarray exists, the output should be 0. The input consists of an integer array nums and an integer limit, where nums can contain up to 100,000 elements, and both the values in nums and the limit can be quite large, up to 1 billion in magnitude. The output is a single integer, representing the length of the longest valid subarray. To understand this better, let's look at a couple of examples. In the first example, the input array is 8, 2, 4, 7, and the limit is 4. Here, the subarray 2, 4 has a maximum value of 4 and a minimum value of 2. The absolute difference between them is 2, which is less than or equal to the limit. Another valid subarray is 4, 7, where the absolute difference is 3, which is also within the limit. However, subarrays such as 8, 2, or 8, 2, 4 have differences greater than the limit, making them invalid. Out of all the valid subarrays, the longest is 2, 4, with a length of 2. Hence, the output for this example is 2. Now consider the second example, where the input array is 10, 1, 2, 4, 7, 2, and the limit is 5. Here, the subarray 2, 4, 7, 2 has a maximum value of 7 and a minimum value of 2. The absolute difference, which is 5, matches the limit, so this subarray is valid. On the other hand, subarrays like 1, 2, 4, 7, or 10, 1, 2 exceed the limit and are not valid. The longest valid subarray in this case is 2, 4, 7, 2, and its length is 4. Therefore, the output for this example is 4. In the third example, the input array is 4, 2, 2, 2, 4, 4, 2, 2, with a limit of 0. When the limit is 0, the only valid subarrays are those where all the elements are the same, because the absolute difference must be exactly 0. For this array, the longest such subarray is 2, 2, 2, which has a length of 3. Thus, the output here is 3. Finally, let's consider some edge cases. If the array contains only one element, the length of the longest subarray is always 1, since there's no difference to calculate. If the limit is very large, it's possible that the entire array is valid, resulting in an output equal to the length of the array. If all elements in the array are equal, the result is also the length of the array, since the absolute difference is 0 for any subarray. On the other hand, if the limit is very small, like 1, and the array contains values that vary widely, the longest valid subarray might only contain a single element, giving an output of 1. These scenarios highlight the importance of carefully considering the constraints and edge cases when solving the problem. To solve this problem, we can start by considering a brute force approach. The intuition behind this method is simple. We iterate over every possible subarray in the input array, calculate the maximum and minimum values for each subarray, and then check if their absolute difference satisfies the given limit. Implementation-wise, this involves two nested loops to iterate through all subarrays, and for each subarray, we compute the maximum and minimum elements. While this approach is straightforward, it is incredibly inefficient. With a time complexity of n cubed, where n is the length of the array, this method becomes impractical for large input sizes. The reason for this inefficiency is that calculating the max and min for each subarray itself requires n time, and with n squared subarrays to evaluate, the total computation quickly becomes unmanageable. Thus, this approach, while conceptually clear, is not suitable for larger arrays and requires optimization. To optimize this, we turn to the sliding window technique, which is particularly well suited for problems involving subarray length constraints. The key insight here is that we only need to maintain a valid window where the absolute difference between the maximum and minimum values is less than or equal to the given limit. By dynamically tracking the max and min values within the current window, we can avoid recalculating them repeatedly. The implementation relies on using two deques, one to maintain the indices of maximum values and the other for minimum values. As we iterate through the array, we expand the window by adding new elements, and we update the deques by removing elements that are no longer relevant for maintaining the max or min. If the difference between the maximum and minimum values in the window exceeds the limit, we shrink the window from the left. This ensures that the window remains valid, and at the same time, we track the maximum size of any valid window encountered during the iteration. The algorithm works by iterating through the array with a right pointer while maintaining a left pointer to define the current window. For each new element, we update the max and min deques by removing elements that are no longer useful. If the absolute difference between the values at the front of the max and min deques exceeds the limit, we increment the left pointer to shrink the window until it becomes valid again. After each adjustment, we calculate the current window size and update the maximum length found so far. This approach is highly efficient, as each element is added to and removed from the deques at most once, resulting in an O(n) time complexity. The space complexity is O(n) as well, due to the storage required for the deques. This method is significantly more efficient than brute force and can handle large input sizes effectively, making it a powerful optimization for this problem. Another approach to solving this problem involves using a binary search-based method with sorted containers. The intuition here is to maintain a dynamically sorted collection of elements in the current window, allowing efficient access to the maximum and minimum values. In Python, the sorted list data structure from the sorted containers module provides this functionality. As we iterate through the array, we add each new element to the sorted list and check whether the difference between the maximum and minimum values in the list exceeds the limit. If the window becomes invalid, we remove the leftmost element to shrink the window. While this approach is more efficient than brute force, with a time complexity of O(n)(log(n), due to the logarithmic cost of insertions and deletions in the sorted list, it is still slower than the deque-based sliding window approach. Additionally, the space complexity remains O(n) for storing the sorted list. While this method is a viable alternative, its performance does not match the efficiency of the deque-based approach. Overall, the deque-based sliding window approach stands out as the optimal solution for this problem. With a linear time complexity of O(n), it is significantly faster than both the brute force method and the binary search approach using sorted containers. Additionally, its implementation is simpler and more intuitive than the alternative methods, while still being scalable enough to handle edge cases and large input sizes effectively. On the other hand, while the binary search approach is a valid alternative, its O(n)(log(n) complexity makes it less efficient for larger arrays. The brute force method, with its cubic time complexity, is clearly impractical and unsuitable for real-world scenarios. By balancing performance, simplicity, and scalability, the sliding window approach with deques emerges as the most effective and preferred solution for this problem. The problem we're tackling involves finding the longest subarray within a given array where the absolute difference between the maximum and minimum elements in the subarray does not exceed a specified limit. To solve this, we could start with a brute force approach. The intuition behind this idea is simple: examine all possible subarrays, calculate the maximum and minimum values for each, and then check if their absolute difference meets the given condition. While this method is straightforward conceptually, it requires significant computation and isn't efficient for larger arrays. To implement the brute force approach, we begin by iterating over all possible subarrays of the input array. This is done using two nested loops. The outer loop sets the starting index of the subarray, and the inner loop determines the ending index. Once a subarray is defined, we calculate its maximum and minimum values by iterating through the elements between the start and end indices. With these values, we compute the absolute difference. If the difference is less than or equal to the given limit, we calculate the length of the subarray and compare it with the current maximum length we've tracked. If this subarray is longer, we update our maximum length variable, which stores the longest valid subarray found so far. After examining all possible subarrays, the final step is to return the value of the maximum length variable as the result. However, it's important to note that this brute force method is highly inefficient due to its cubic time complexity, O, n cubed. This is because generating all subarrays takes O, n squared, and calculating the maximum and minimum values for each requires an additional O, n, for every subarray. While this approach works for smaller arrays, it becomes impractical for larger inputs. The inefficiency stems from the repetitive calculation of maximum and minimum values for overlapping subarrays. To summarize, the brute force method uses basic arrays for input storage and simple variables to track the maximum and minimum values, as well as the longest valid subarray length. To better understand the brute force approach, let's walk through an example. Consider the array 8, 2, 4, 7 with a limit of 4. Starting with the first index, I equals 0, we look at subarrays ending at different indices. For j equals 0, the subarray is 8, where the maximum and minimum values are both 8, resulting in a difference of 0, which is valid. For j equals 1, the subarray becomes 8, 2, where the maximum is 8 and the minimum is 2, giving a difference of 6, which exceeds the limit and is invalid. We continue similarly for other subarrays starting at I equals 0, then move to subarrays starting at I equals 1, I equals 2, and so on. Throughout this process, we track the maximum valid subarray length by comparing the lengths of all subarrays that satisfy the condition. To overcome the inefficiencies of the brute force approach, we can consider optimizations. One powerful technique is the sliding window, which avoids recalculating the maximum and minimum values for overlapping subarrays. Instead, the window dynamically adjusts its size as we iterate through the array, ensuring that it only contains elements that satisfy the condition. Additionally, efficient data structures like deques can be used to maintain the indices of elements in the window, allowing us to compute maximum and minimum values in constant time. By combining sliding windows with deques, the time complexity can be reduced to O, n, making the solution scalable for larger arrays. It's also important to handle edge cases, such as empty arrays, single-element arrays, or extreme values of the limit. While the brute force approach provides a foundation, these optimizations are essential for practical and efficient problem solving. Here, we begin by importing the deque class from the collections module, which will help us efficiently maintain the maximum and minimum elements within a sliding window. Inside our solution class, we define the method longest subarray, which takes the input list nums and an integer limit. To track the maximum and minimum values in the current window, we initialize two deques, max_deque and min_deque. Additionally, we set up a left pointer, which represents the start of our sliding window, and a variable max_length to keep track of the longest valid subarray we've encountered so far. Now, we iterate through the nums array using the right pointer, which represents the end of the sliding window. For each element, we first update our max_deque to ensure it maintains a descending order of values. We do this by removing indices from the back of the deque while the current number is greater than or equal to the value at those indices. Then, we append the current index to the deque. Similarly, we update our min_deque to maintain an ascending order by removing indices from the back while the current number is less than or equal to the value at those indices, and we append the current index as well. After maintaining these deques, we check if the absolute difference between the maximum and minimum values in our window exceeds the limit. If it does, we shrink the window by moving the left pointer forward. As part of this process, we also ensure that the indices in our deques remain within the bounds of the window by removing indices that fall behind the left pointer. If the maximum or minimum indices in the deques are now out of range due to the left pointer moving forward, we remove them from the front of their respective deques using the pop-left method. This ensures that both deques only contain indices within the current window. Once the window is valid again, we calculate its length by taking the difference between the right and left pointers, adding 1 to account for zero-based indexing. We then update the max_length variable to store the maximum length encountered so far. This process continues for every element in the nums array. Finally, after the loop completes, we return max_length as the result. This value represents the length of the longest continuous subarray where the absolute difference between the maximum and minimum values does not exceed the given limit. By utilizing deques for efficient tracking of max and min values, this approach achieves a time complexity of O, n, making it highly efficient for large input arrays. Here, we begin the implementation of a solution for finding the longest continuous subarray where the absolute difference between any two elements is less than or equal to the given limit. We start by defining a method longest subarray, which takes an integer array nums and an integer limit as inputs. To efficiently manage the maximum and minimum values within the current window, we utilize two deques, maxDeque to maintain indices of the maximum elements in descending order, and minDeque to maintain indices of the minimum elements in ascending order. These deques help us dynamically track the bounds of the window. We also initialize two variables, left to track the starting index of the sliding window, and maxLength to store the maximum length of a valid subarray. Next, we iterate through the array using a right pointer, expanding the window one element at a time. For each element, we update the maxDeque by removing indices from the back where the corresponding values are less than or equal to the current element, ensuring the deque remains in descending order. Similarly, we update the minDeque by removing indices from the back where the corresponding values are greater than or equal to the current element, maintaining ascending order. After these updates, we check if the absolute difference between the maximum and minimum values in the window exceeds the limit. If it does, we increment the left pointer to shrink the window from the left. If the left pointer moves forward, we also ensure the deques remain valid by removing any indices at the front that are out of bounds, meaning they are less than the current value of left. This ensures that both deques only contain indices within the current window, allowing us to efficiently retrieve the maximum and minimum values. Once the window is valid, we calculate the length of the current subarray as right, left plus 1 and update maxLength if this length is greater than the current maximum. By iterating through the array in this manner, we dynamically adjust the window size to maintain the constraint while keeping track of the longest valid subarray. After the loop finishes, we return maxLength as the result, which represents the length of the longest subarray that satisfies the absolute difference condition. This approach ensures optimal performance with a time complexity of O(n), as each element is processed at most twice, once when added and once when removed from the deques. We'll start by examining the first example, where nums is 8, 2, 4, 7, and the limit is 4. Initially, we set up two deques, max_deque and min_deque, both of which will help us efficiently track the maximum and minimum values in our sliding window. We also define two variables, left, which represents the start of the window, and max_length, which keeps track of the longest valid subarray length we've seen so far. Both are initialized to 0. Now, let's begin iterating over the array with the right pointer. At right equals 0, the current number is 8. Since the window only contains this one number, we update both the max_deque and min_deque to include the index 0. The window is valid because the absolute difference is 0, which is less than or equal to the limit. As a result, we calculate max_length as 1, which represents the length of the current window. Next, at right equals 1, the current number is 2. We add its index to the max_deque, and since 8 is still the largest value, we keep it in the deque. For the min_deque, we remove the index of 8 because 2 is smaller, and then add the index of 2. However, when we check the window's validity, the absolute difference between 8 and 2 is 6, which exceeds the limit. This means we need to shrink the window by moving the left pointer to 1 and removing the index of 8 from the max_deque. The updated window is now valid, but max_length remains 1 as the current window length is also 1. At right equals 2, the current number is 4. We add its index to the max_deque, and since 4 is greater than 2, we remove 2's index, leaving only the index of 4 in max_deque. For the min_deque, we simply add the index of 4 because it does not disrupt the order. The absolute difference between the maximum and minimum values in the window is 2, which is within the limit, so the window is valid. We update max_length to 2, as the current window length is now greater than the previous maximum. Now, at right equals 3, the current number is 7. We update the max_deque by adding its index, and since 7 is now the largest value, we remove the index of 4. The max_deque now contains only 7's index. For the min_deque, we remove the index of 2 because 7 is much larger, and we add 7's index. The absolute difference between the maximum and minimum values in this window is 3, which is still within the limit. This means the window remains valid, and we update max_length to 3, reflecting the current window length. The final result for this example is max_length equal to 3. In the second example, nums is 10, 1, 2, 4, 7, 2, and the limit is 5. Once again, we start with empty deques and initialize left and max underscore length to 0. At right equals 0, the current number is 10. Since this is the only number in the window, both max underscore deque and min underscore deque are updated to include its index, and the window is valid. We set max underscore length to 1. At right equals 1, the current number is 1. We update the deques accordingly. For max underscore deque, 10 remains the maximum, while for min underscore deque, we remove the index of 10 and add the index of 1. However, the absolute difference between 10 and 1 exceeds the limit, so the window is no longer valid. We adjust the window by moving the left pointer to 1, which effectively removes 10 from the window. The window becomes valid again, but max underscore length remains 1. This process continues as we iterate through the array. At each step, we ensure the window is valid by adjusting the left pointer as necessary. When right reaches 5, the longest valid subarray has a length of 4. This is the final result for this example. In the third example, nums is 4, 2, 2, 2, 4, 4, 2, 2, and the limit is 0. Here, the limit of 0 means that the absolute difference between any two numbers in a valid subarray must be 0. This implies that only subarrays where all elements are equal can be considered valid. For this array, the longest such subarray has a length of 3, consisting of 3 consecutive 2s or 3 consecutive 4s. The final result for this example is max underscore length equal to 3. The time complexity of our solution is O, n, where n is the length of the input array nums. Let's break this down step by step. First, we have the outer loop, which uses a sliding window technique. In this loop, the right pointer iterates from the start to the end of the array, processing each element exactly once. This contributes O, n, to the overall complexity. Then, there's the deque operations, where we maintain two deques max underscore deque and min underscore deque to store indices of elements in a way that allows us to track the maximum and minimum values within the window efficiently. Each element is added to a deque and removed from it at most once. This means all deque operations combined across the entire array also contribute O, n. Together, these steps give us a cumulative time complexity of O, n, so far. Next, we examine the inner while loop, which is responsible for shrinking the window when the absolute difference between the maximum and minimum values exceeds the given limit. The left pointer moves forward to make the window valid again, and just like the right pointer, each element is processed at most once. The total number of iterations of this while loop is therefore also bounded by n, contributing another O, n, to the time complexity. When we combine all these steps, the outer loop, deque operations, and the window shrinking process, the total time complexity becomes O, n, plus O, n, plus O, n, which simplifies to O, n. For the space complexity, the primary factor is the space used by the two deques. In the worst case, either deque could store all indices of the input array, such as when the array is strictly increasing or decreasing. This means the space complexity contributed by the deques is O, n. Additionally, the algorithm uses a constant amount of auxiliary space for variables like left, right, and max underscore length. These variables require O1 space, which is negligible compared to the space used by the deques. Combining these, the overall space complexity of the solution is O, n. Comparing this with the brute force approach, a naive solution would involve generating all possible subarrays and calculating the maximum and minimum values for each one. For an array of size n, this means roughly n squared subarrays, and finding the max/min for each would take O, n, time. This results in a brute force time complexity of O, n cubed. However, the space complexity for the brute force method is constant, or O1, since no additional data structures are used. Our optimized approach, which uses sliding window and deques, significantly reduces the time complexity to O, n, while only slightly increasing the space complexity to O, n, making it far more efficient. To solidify the claim of O, n, time complexity, consider this mathematical proof: each element in the array is processed exactly twice in relation to the deques. Once when it is added to a deque, and once when it is removed. With n elements in the array, this means the total number of deque operations is at most 2n. Other operations, like comparisons and updates, happen in constant time. Therefore, the overall time complexity remains linear, O(n). This efficiency stems from the careful design of the algorithm, where redundant calculations are avoided and every operation is bounded by the size of the input. When solving this problem, there are a few common mistakes to watch out for. First, many solutions fail to handle edge cases properly. For example, consider an array with just one element, or one where all the elements are identical. Another common scenario is when the limit is 0, which imposes stricter constraints on the absolute differences. To avoid these pitfalls, always test your code with edge cases, including both the smallest and largest input sizes allowed by the problem. Another issue is using the wrong data structure. For instance, problems that require dynamic tracking of subarray properties, such as the maximum or minimum value, often demand more efficient structures like heaps, sliding windows, or monotonic queues. Using an unsorted list here would lead to poor performance. Additionally, brute force approaches, although intuitive, are rarely efficient for larger inputs. For example, iterating over all possible subarrays can lead to O(n)³ time complexity in some cases, which is impractical for large inputs. Techniques like sliding windows, binary search, or prefix sums can help optimize such solutions. Finally, overlooking constraints in the problem statement is another frequent mistake. Constraints like a sorted input or the presence of unique elements often simplify the problem significantly. By carefully analyzing the constraints, you can avoid overcomplicating your solution and arrive at a more efficient approach. Another frequent source of errors is off-by-one mistakes, especially when handling subarray boundaries. These errors occur when indices are either incorrectly included or excluded, leading to incorrect results. To mitigate this, double-check all index operations and verify your code with small test cases to ensure correctness. From an interview perspective, it's important to recognize recurring patterns in array problems. For example, sliding windows are often used for subarray problems, binary search is effective when monotonicity is involved, and hashing or prefix sums are great for efficient lookups. When discussing your solution, always explain the trade-offs between different approaches, such as the balance between time and space complexity. This demonstrates a deeper understanding of the problem. Additionally, dry running key test cases during the interview can help catch errors early and show your thoroughness. Lastly, always articulate the time and space complexity of your approach. For example, if you propose a brute force solution with O(n)³ complexity, explain why it won't scale for larger inputs, and suggest a more optimized approach if possible. This problem shares similarities with other questions that you might encounter. For instance, LeetCode 239, Sliding Window Maximum, teaches how to efficiently track the maximum value in a sliding window using a deque. Another related problem is LeetCode 209, Minimum Size Subarray Sum, which is a classic example of applying the sliding window technique to meet specific subarray constraints. LeetCode 325, Maximum Size Subarray Sum equals k, demonstrates the use of prefix sums combined with hashing to solve subarray sum problems. Similarly, LeetCode 862, Shortest Subarray with Sum at least k, is a more advanced variation that combines sliding window and monotonic deque techniques. Beyond these, there are alternative approaches to solving subarray problems. For example, using a sliding window combined with sorted data structures like a tree set provides an elegant solution with O(n) log n complexity, but it does come with additional space requirements. Alternatively, monotonic queues can achieve O(n) time complexity for problems that involve finding the maximum or minimum values in a sliding window. However, implementing monotonic queues can be more challenging due to their complexity. There are additional methods to consider for solving subarray problems. Binary search with prefix sums, for instance, is particularly useful when the problem involves constraints like monotonicity. While this approach can be powerful, it requires pre-processing the array and demands careful implementation to ensure correctness. Another option is the heap-based approach, which is well suited for dynamically tracking the maximum or minimum values within a subarray. However, maintaining a heap introduces additional overhead, making it less efficient compared to some other methods. Each of these techniques has its own trade-offs, and understanding when to use them is key to crafting efficient solutions. By mastering these strategies, you'll be better equipped to tackle a variety of subarray problems effectively. Great job! In this session, we learned how to solve the longest continuous subarray with absolute diff less than or equal to limit using a sliding window approach. We discussed time and space complexities and explored key takeaways, including the importance of sliding window techniques and dynamic range management. Keep practicing, and don't forget to like and subscribe for more coding insights. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!